morning. We continue with our discussions on combustion instability, and what we did in the last class was we said whenever we have wave modes in the chamber, you have regions wherein you have pressure antinodes, you have pressure nodes, you have pressure antinodes, and this could depend on the harmonic what we have. In the fundamental, I will have, let us say if this is a closed end, I have a pressure antinode. If this is a closed end over here, I have a pressure antinode over here, and in between I have a pressure node. If I have higher harmonics, I have a set of a pressure antinode coming here, a pressure node here, pressure node here. So also wherever we have pressure antinode, you could have velocity nodes and vice versa. Now what is the inference of all this? Let us say at a particular point I have a pressure perturbation P out of the, let us say, standing wave. I want P prime to increase. What can cause an increase in P prime? If I were to add mass, let us say m dot prime to P prime, in other words I have a volume, the volume has a pressure P prime, I add some fluctuating mass to it, then automatically that means I have an oscillation of P prime over here. I add mass at the moment of maximum P prime, therefore my oscillation goes up. I again add mass over here, pressure goes up. If I were to have a condensation or a rarefaction over here, at this point I sort of add mass in the negative direction, that means I remove mass, my amplitude goes up. Therefore the object of adding mass when the pressure perturbation is a maximum can give rise to a higher value of pressure. All what I am looking at is I am having a pressure perturbation P prime. If I add mass in the same phase as pressure, then apparently maybe the addition of the mass perturbation to the pressure perturbation could result in amplitude of the pressure perturbation going up. Therefore I tell myself, first point I say is, if mass perturbation or I add mass at the same phase as a perturbation in pressure, then the pressure perturbation could increase. In other words, I am looking at the product of something like mass perturbation, let us say m dot prime, and the value of P prime, which can lead to growth of the wave motion. Right. See, instead of adding mass, let us say the second point I consider is, supposing I have, see we considered velocity changes, we considered pressure changes. Whenever I have pressure changes, I could also have temperature changes. Therefore if I could add, if heat could be added, heat perturbation, let us say Q prime, Q dot prime is added when T prime is maximum, or rather I have a temperature fluctuation like this. I add heat when it is maximum, well my temperature fluctuation will increase. I add still further heat, my temperature fluctuation will increase. Therefore heat perturbation in phase is added, where in phase, let us say, that is important, when in phase with T prime is what will give me a higher value of this. Therefore I can say my zone of interest could also be, if I add heat perturbation, because in a chamber, yes I am generating heat, I have heat perturbation, rate of heat release perturbation, along with let us say a temperature perturbation, and this should also, if this is in phase with this, well the oscillation could increase. See, we considered pressure, I considered temperature. Now when I say third one, if I have velocity perturbation, supposing we said, well my velocity could also be in this particular form, I could have velocity like this. What should I do if I have to increase the magnitude of velocity perturbation? Velocity perturbation is V prime, therefore if momentum, if rate of change of momentum, that means At this point I put more momentum into it, well, could increase, here I remove, here I add. That means if the rate of change of momentum could be put in phase with velocity perturbations, then my velocity perturbations could also increase. In other words, the third one I can put is if rate of change of momentum is force, if force perturbations could be added in phase with velocity perturbation, that means I just say V prime, then the magnitude of V prime will increase, and therefore the quantity there could be force perturbation multiplied by velocity perturbation. Therefore, why I tell myself, well, pressure perturbations can increase if I could add mass perturbations in phase with pressure perturbations. Temperature perturbations could increase if I could add heat in phase with this. Velocity perturbations could add if I have rate of change of momentum in phase with this. What is the units I am talking of? Force Newton, Newton meter per second, Newton meter per second, or rather joules per second. This gives me the unit of watts. If I were to put a unit over here, what is the unit I get over here? Let us put the unit over here for m dot p. M dot p is so much kilogram per second. Now I have pressure here, Newton per meter square, and if I have to have unit of work, because basically I am doing work to increase the perturbation, then maybe I must divide it by the mean density, and if I divide it by mean density I have kilogram per meter cube, and therefore meter come here, kilogram gets cancelled, this also becomes joule per second or watts. Therefore, I can represent m dot p in terms of a function which does work on the system in terms of rate of work on the system as maybe m dot prime p prime divided by the mean density. How do I represent this? Q dot has energy per unit time, T prime is here, it's an addition. Maybe if I were to write in terms of so much watts or so much joules per second, T prime divided by the normal temperature, well, this also has units of W. Therefore, I can say if I were to add power as a product of force in phase with velocity, add power in terms of heat transfer as a function as in phase with temperature perturbation, add mass in phase with pressure perturbation, well, I could amplify it, and all these three things has been put together beautifully by one person by name Chu. He worked for some time in the area of combustion instability, and he put all these things together and he called it as a parameter sigma, and he said the power which adds to the magnitude of oscillations could be represented by, let us say, m dot prime p prime by rho. This is a mass release exciting the pressure oscillations, maybe q prime q dot prime into T prime divided by, let us say, the mean temperature, could be the mean density over here, plus you have force prime into the velocity prime is the parameter which causes or which puts power or energy into the wave motion and causes wave to grow. And how do you put power? It could be from mass, it could be from heat transfer, it could be from rate of change of momentum, and we have all the three things in a rocket motor. We are generating heat, therefore heat could excite the oscillation to grow, we could have mass concentration is being added, we are adding force, we are having rate of change of momentum, it could add, therefore all these three parameters are important. But in a rocket chamber again, we also have boundary layer, it was made, this point was made earlier, it could cause viscous drag, a wave when it is travelling gets retarded by the boundary layer. Maybe if I have solid propellants, I have particulates, particulates will cause drag, it will break up the wave. It could have maybe the flow turns in the, when a flow turns it loses energy, and therefore there are also some factors, just like I have sigma watts adding energy, I could also think in terms of some capital phi which removes energy from the wave. That means I have sigma watts coming from mass release, from heat release, from force, and similarly I have some quantity which removes it, and the net value, it depends on sigma minus phi taken over the whole volume, and in a one cycle of oscillations is what tells me whether the wave will grow or not. If this is positive, well, I am adding more and more mass and it will grow. If this is there, maybe it will keep coming with respect to time like this. And with this was something which was beautifully illustrated, and let us follow this up and come to some conclusions. We are just now telling heat addition in phase with temperature oscillations, that is rate of heat perturbation or disturbances in phase with temperature in phase with temperature fluctuations. Rather, what we are saying is P prime in phase with T prime. I am sorry, heat perturbations means Q dot rate of heat in phase with T prime. But you know, we are not really measuring temperature fluctuations. Can I therefore put it in terms of pressure fluctuations is what we can readily measure, and that is what we have been talking all along. Therefore, how do I convert temperature fluctuations into pressure fluctuations? Well, we assume that the system is adiabatic. Any acoustic wave is adiabatic because the pressure perturbations are small. Therefore, I can write, well, P divided by V to the power gamma is a constant. I also know from the gas equation PV by T is a constant. I combine these two together and this gives me P to the power gamma minus 1 by gamma by T is a constant. We have done this earlier. How did we do? We say P to the power gamma, V to the power gamma, T to the power gamma is there, and therefore I divide one by the other, I get this expression. And if I were to take this expression and differentiate it, let me do it on the other side. I get P to the power gamma minus 1 by gamma divided by T is a constant. I take the logarithm and I say gamma minus 1 by gamma into ln of P minus ln of T is ln of a constant. I differentiate it, I get gamma minus 1 by gamma into ln P, that is P prime divided by P, is equal to T prime divided by T. Ln C is a constant, this is dt by T, dt is T prime, perturbation, this is the usual value, and therefore now I get T prime is equal to gamma minus 1 divided by gamma into P prime divided by P. T prime is equal to gamma minus 1 by gamma into P prime divided by P into T. Let us substitute it in the value what we had for the case of temperature. What did we tell? That the value of sigma or the energizing parameter is equal to something like, we talk in terms of Q prime into T prime divided by T, and therefore now I say Q prime and I take the value of T prime as I get here, T prime by T is equal to gamma minus 1 by gamma into P prime by P, and therefore now I find heat release, when that is a perturbation in heat release, when it is in phase with the changes or perturbation in pressure, would also cause an oscillation just the same way as heat release in conjunction with temperature will cause. This is physically, we know when I add heat the temperature increases, but this is not so apparent to us, and this tells us that heat release in conjunction with a pressure perturbation will lead to energy being given to the wave motion, or the oscillations will grow, and this is the famous hypothesis of Rayleigh. It is known as Rayleigh principle, and all Rayleigh principle says is, if I add heat at the moment of the greatest compression or I remove heat at the moment of the greatest condensation. By condensation in the old days it meant rarefaction, then an oscillation will be encouraged. I will repeat it. Rayleigh principle is extremely important for the following, that it helps us to understand the role of heat release in causing an oscillation. And what does the Rayleigh theory tell you? It tells you if I have pressure oscillations, if I add heat at the moment of greatest pressure compression or I remove heat at the moment of greatest, then the oscillations are encouraged, that means oscillations will grow. This looks very apparent, but this is very basic to our thinking. Let us illustrate this through a small example. What I do is I take a tube. Now a tube is open at both ends, therefore I will get something like a velocity antinode here, or since the pressure is same here and here, the velocity antinode corresponds to a pressure node here. Similarly over here I get a velocity antinode, or let us say a pressure node over here, and at the center I get a pressure antinode, I get a velocity node, and let us add heat to this and see whether the principle really works. And the principle is demonstrated in a particular vertical tube which people call as Ricci tube. I thought we must take a look at it such that maybe when I add heat at some location, I will find that automatically the tube starts singing or tube starts to make a noise, and that is what we will do now. Let us just add heat, and for this purpose maybe we will take a sparkler, we will add heat through a sparkler because we need some substantial amount of heat. Let us do that. As I keep telling you, to make a fire it is not that easy. Like here we had a pyrogen igniter, we need to build a small fire to make a slightly bigger fire and still make a bigger fire. So also we had to light a candle to get a sparkler to go. With a matchstick it is little difficult, especially in an AC room. Well, this is a sparkler going. Now I want to ignite a slightly bigger sparkler. I use this because it is more energetic. Now all what I do is I take this vertical tube, this is the tube I have, and now I hold it vertically, I introduce the you hear the noise, right? Noise comes down. At the location where I make a mark here, which is 1/4 the length, it makes maximum noise, and then as I keep coming down, the noise keeps coming. The question is, you just had a tube in which there is hardly anything, and all of a sudden it starts making a noise. And what is noise? Noise is sound. That means I am causing pressure perturbations, and this is what we would like to understand a little bit more. Therefore, all what we are saying is, let me invert it. If I hold it horizontally and if I add here, nothing happens, very little, but because I am having some air motion, but I do not get the type of sound what I normally get when it is vertical, when it is much louder, and therefore the question is, what causes this particular sound to come? And this is what maybe we will try to understand, and if we can understand this, well, I think we have understood a major part of the combustion instability thing what we want to do. Well, it is almost over. Therefore, what is the experiment which we just did? Let's try to analyze it. We found that the tube in the vertical condition made lot of noise, whereas in the tube which was in the horizontal direction also made some noise, but was not as high as in the vertical tube. What did we do? We put some heat source at some location. When I put some heat source, hot gases are convected up. Hot gases are convected up, they meet this boundary wherein I have the velocity node, it gets reflected, I get something like a pressure antinode over here, I get a pressure node here, I get a velocity antinode here, pressure node over here. And what is happening? At this central place between these two, I have something like I still have pressure oscillations and velocity oscillations in the standing wave mode, because my tube diameter is small, I do not give room for the tangential and radial modes, and therefore the location where I have significant velocity, I have lot of energy being added from the sparkler into the flow medium. It is also where the pressure is significant, and therefore at this location when I put my sparkler, I have maximum noise. And what is maximum noise? I have maximum values of pressure perturbation. Therefore, putting a heat source has caused the pressure magnitudes to jump up, and that is what happens in a rocket chamber. What happens in a rocket chamber? You have the gas flow, I have pressure antinode, pressure node here. Supposing I put a heat source at the location of maximum pressure, well, my pressure amplitude keeps increasing and my amplitude goes up. And this is precisely the principle. In this case it is convective. I had an open tube to do a simple experiment. If I put a horizontal tube, well, my mass generation is large, therefore some gas goes up, I have the oscillations coming like this, and when I put it here I still get some sound here. But normally the sound in this case was much higher, the reason being I am able to get the convective motion to give me a stronger wave interaction, whereas in this case the velocities are much lower, because here I have the buoyancy effects which help me, in which case it does not help me here. Here I will get mixed modes. If you had really looked at the sound, I would have got something like a radial modes and other modes coming here, whereas here it is purely axial. If this part is clear, let us quickly go through what little we have understood so far. Well, we tell ourselves it is not only that. Long back, in UK, which was the hub of all experimentations in engineering, you had this philosophical society, and in this society every weekend people used to go and display whatever they have learned. This particular person, Tyndall, he was in 1897, he demonstrated when he played the piano, when he struck the piano notes, the flame would just jump up, and the moment he stopped it, it used to come back again. But when the piano is not there, you would get a steady flame. In other words, acoustics like what we are showing, that is the heat addition or the acoustics is affected by this, and that happens because of the pressure perturbations in resonance or in phase with the pressure or velocity fluctuations, that is heat release fluctuations. In here he is striking a note, he is generating the waves which is going up and down, and you have an astonishing variety of process. Not only that, in fact Tyndall at that time thought maybe by looking at a flame, and when he sings something, maybe by looking at a flame even a person who cannot hear music will be able to appreciate the signals which are coming from a flame and will be able to appreciate the music. That was his thinking. Even a person who cannot hear maybe visually can see a singing flame and thus appreciate whatever he was doing. Well, what is it we have been telling? Now let us put things together. I have a solid propellant rocket end burning grain, this is the region of closed end, I have a pressure antinode, the energy release or the heat release is in phase with the pressure antinode, I could have the thing go up. In the case of a liquid propellant rocket, I inject, I have this near the head end, maybe if I have maximum pressure oscillations here, I could still have oscillations to grow. But one thing which is important, which we have not said so far, is we have told ourselves, well, I have something like a frequency. I have standing waves of a given frequency. We also tell, well, the heat release or the mass release or the velocity changes should be in phase. That means the frequency of the heat release must also be at the same frequency. If the frequency of the heat release is different from the frequency of the standing wave, maybe once I add heat, the second time I add heat, it is not possible to get it. Therefore, it is essential that the frequency of heat release should also be the same. And therefore, we talk in terms of, it is not only what I am showing here, that it is just not a dumb heat release, but the frequency. If I had a slightly shorter Rich-K tube, it would have made very much higher frequency. Such high frequency we may not be able to hear even, and that is why I chose this particular length of 1.2 meters or so. Well, this is all what I showed you earlier. Maybe rate of mass addition perturbations in phase with pressure will lead to enhancement. Similarly, rate of heat release fluctuations in phase with temperature fluctuations, and from this we derived the Rayleigh criterion for heat release. Similarly, you have force perturbations in phase with velocity perturbations, or body force or periodic body force in phase with velocity fluctuations, giving power to increase the phases, and we put all these things together. We had a dissipation term, an energy supplying term over a cycle of oscillations. If it is greater than 0, well, an oscillation could occur. The only thing which is important for us to remember is Q prime and P prime should have the same frequency, otherwise it is just not possible to have this, right. I think that is basic to it. This is what we just now saw, thermoacoustics. Maybe we put a heat source here and we could hear the sound, that means pressure perturbations growing. And if I have a solid propellant, these are all AP particles in the resin over here, I have a flame standoff here, aluminum particles are burning here, it dampens the wave just like boundary dampens the wave, and therefore you have phi minus sigma which leads to this. If I have a liquid propellant rocket, well, I have injector, I have zone of heat release like this, therefore I could have tangential and radial modes also causing this, and you could end up having pressure perturbations. Well, this is all about combustion instability, and now I should be able to put things together in the next 20-25 minutes together. Let us now take review of what we have done so far. Let us say, yes, we have understood what combustion instability means. We started with the thing with respect to maybe feed coupled oscillations, in which we said P is a function of time alone. Then we talked in terms of the wave mode. I should have written here maybe the bulk mode, and in the wave mode I have P as a function of distance and a time which is varying. Here you form standing waves. If heat release is at the same frequency, and because it is unsteady heat release and it is in conjunction at the point of maximum pressure perturbation, you add heat, well, I get an oscillation. It need not be from heat alone, it could be from mass addition also in phase with a pressure perturbation, or it could also happen with force, that is a body force perturbation in conjunction with a velocity perturbation. And now we know, well, why does combustion instability have to occur? Well, we have energy being supplied by the combustion process, it drives the pressure, it drives the oscillatory pressure. In some cases the pressure perturbations keep on increasing. Therefore, now let us put the subject in proper focus. We tell ourselves first, well, a rocket is a small chamber, it generates lot of heat compared to, let us say, an aeroplane gas turbine chamber or a car whose rate of heat release is something like 0.1 kilowatt per centimeter cube, much lower than that, compared to a plane which is of the order of 5 kilowatt per centimeter cube. A rocket gives something like 100 kilowatts to something like a world's, I showed you that RD 170 engine, we said it burns liquid kerosene and liquid oxygen at a pressure of almost, we said, around 245 bar, and we said this was a very powerful stage combustion engine. the type of energy what we are getting is something like 1000 kilowatt per centimeter cube, and whenever we talk of something like an explosion, this is the type of energy release what we get. Therefore, even a minuscule small amount of this energy, if it gets into the wave mode, well, I could start getting some oscillations. To be able to figure out how much of the heat release gets into the oscillation, we have specific devices. Now, this is something which we must know. Supposing I want to measure the growth constant of a propellant. Supposing I have, let us say, a solid propellant in a chamber. I have the propellant which is burning radially over here. I find that the propellant which burns here is at a pressure antinode. At the center it is a pressure node corresponding to fundamental. Here it is near to a pressure antinode. Therefore, different points are at different locations. But what I am interested in, maybe I am interested in the value of phi minus sigma. If it is greater than 0, well, it is unstable. And what did we say? Integral over the volume over a cycle of time, that means over a cycle of oscillations must be greater than 0, or rather I can reduce this form as the growth constant. That is, if I were to look at a propellant and evaluate whether I can evaluate, we said oscillations can be put in terms of growth plus the frequency to the power t. This tells me the rate at which oscillations are growing. Can I measure this growth constant of a propellant? To be able to measure this, I make a tube. I make the length of the tube such that I am getting the same frequency as my chamber over here, standing wave mode of the chamber. I make the length, and how do I say in the fundamental, this length gives me this frequency. I put a slab of propellant at the end, that means at the pressure antinode. I can get the precise value of the pressure antinode. I ignite it, I burn it, and what is it I observe? That means I have something at the antinodes. I put the solid propellant, the length is L for the given frequency. I also put a tank over here such that I can maintain the pressure at the level of the pressure in the chamber. We would like to know the rate at which the oscillations grow. Rather, we are interested in finding out the value of p prime as a function of p hat, and since we are interested in the growth of these oscillations, we are interested in finding out the growth constant alpha, and this, when the oscillations grow, is positive, and that is what we measure in a T burner. Let me come back to this. In a T burner, as you see here, you have a tube like this. You have the propellants at the ends of the tube. At the center you have a hole, and we told ourselves earlier that at the ends you have pressure antinodes. At the center you have a pressure node. Therefore, at the pressure node portion you connect it to a huge surge tank, by which, by keeping a pressure of gas here, you can maintain the pressure in the tube to be at any value what we want. We also would try to keep the length of the tube corresponding to the frequency of interest. We have already seen this earlier, namely the length of the tube will control the frequency of the oscillations which take place. Therefore, when the propellant is ignited at the ends and you have some disturbances taking place, the waves tend to grow as shown over here till the time the propellant burns, and when the propellant gets burnt out, the damping effects in the chamber cause the wave amplitudes to decrease and it comes down. In other words, the waves grow in amplitude and thereafter the waves decrease in amplitude, and this I show in this particular figure. This is an experimental plot wherein this is your T burner, the propellants are kept at the ends, I have the surge tank mounted at the center, and this is the way the waves grow, reach a maximum value, and once the propellant has burnt out, the pressure amplitude decays down. Now, if I plot these, the change of pressure amplitudes as a function of time, and maybe on a log plot or otherwise, I find yes, this is the rate at which these are the pressures at the different times, or pressure is increasing and the pressure is decaying like this. In other words, I can sort of measure or determine the rate at which the growth of oscillations take place, namely the alpha in p prime is equal to p hat alpha t, and also the rate at which it is decaying. Using this, I go to the next one, namely I show here the growth of oscillations, the magnitude of the log pressure versus time increases, and therefore I can determine my growth rate. I would like to use the growth rate as I measure in the previous case. In this particular T burner, it is in the form of a center, the top of a T, and the portion, the hub, that is the T, comes over here connecting to the surge tank. I would like to make use of the growth constant as measured in the T burner to be able to predict the stability of combustion in a solid propellant rocket. To be able to do that, I have one more problem to reconcile with, and that has to be sorted out. Namely, in a T burner, the propellants burn at the antinodes, but in this particular case propellants are burning at both the antinode as well as in the node region and in the different regions. Therefore, I have to measure, or I have to correlate the growth constant of oscillations in the motor, namely alpha, with respect to what I measure in a T burner. For this case, I go ahead, I define something like an acoustic conductance ratio of the burning surface, and I derive an expression for the growth constant in terms of the energy release per unit time divided by twice the average energy, and then evaluate in a T burner the value of K, substitute it in the expression for the waveform in this, and get the value of the growth constant in the particular rocket motor. In other words, I am able to get the growth constant in the rocket motor using this expression. I also measure the losses, like the losses which I measured in the T burner, namely the losses could be from the nozzle, wherein some element of acoustic energy gets radiated out. I could have particles of aluminum in the rocket motor, which again leads to dissipation of energy and reduction in the, or decay constant, and therefore I sum up the value of the growth of oscillations due to the propellant, and I take all the decay effects, namely the loss effects, and if the net value of alpha is less than 0, I say, well, alpha is less than 0, it is negative, and therefore the motor is stable. If alpha is greater than 0, well, the oscillations keep growing and the motor becomes stable. And this is the way we make use of the T burner to evaluate the growth constant with the propellant kept at the antinode position, convert the growth constant for a motor, for which case I take the whole wave, get the net value of the growth constant for a motor, and then subtract the losses due to the different dissipative effects and find out the net value of alpha. And if the net value of alpha is less than 0, we say that the motor is stable because the energy in the waves is less, or the pressure amplitudes keep decreasing, while if it is greater than 0, the motor becomes unstable. We must keep one thing in mind: whenever we talk of oscillations, whether it is in a T burner, whether it is in a rocket, they are all at a particular frequency. I get a spike over here, this tells me the pressure amplitude as a function of frequency. I get pressure amplitudes at a given frequency, and they are not distributed over a range of frequencies. In other words, these are unique to particular frequencies, and I evaluate the growth constant in a T burner at the frequency of the rocket motor, use that value to be able to get the growth constant in the motor, subtract the losses, and thereafter determine the stability of the motor. What I was trying to tell you was, under certain conditions, depending on the chamber conditions or the rate at which droplets are introduced, you have zone at which energy is getting released. If I have a pressure antinode or a velocity antinode wherein the heat transfer is higher, or a pressure antinode is in the same phase as the heat release, well, my oscillations will grow, and such type of oscillations are also referred to as acoustic oscillations. Why acoustic oscillations? Because of the acoustics, that is the sound waves getting reflected, forming a standing wave, and instead of calling it as wave mode oscillations, it is also known as acoustic oscillations. Well, what is the characteristic of acoustic oscillation? The pressure perturbations are small compared to the mean value of pressure. Like when I talk, hardly it is all isentropic, the pressure changes are very small, that means we are talking of very small value, but under certain conditions the oscillations become non-linear. What do you mean by non-linear? In a linear process I can decouple this, I can say P prime happens at a frequency omega 1, the first fundamental, the higher harmonics omega 2, omega 3. I can write the equation as maybe P1 into P prime 1 sin omega 1 t plus P2 prime sin omega 2 t plus I can write P3 sin omega 3 t and so on, and these are all clearly they can be removed because it is a linear system. But when it becomes non-linear, the frequency here could interact with the frequency here and I could get new set of process. That means the wave interaction could still happen in a non-linear mode, and if it happens in a non-linear mode, what happens? Supposing I were to say, well, this is my pressure, there is let us say pressure perturbation over here, and this is my response, and how do I define response? I can say response is equal to the rate of mass fluctuation divided by the mean value divided by the pressure perturbation divided by the mean value, let us say P0. What happens if I plot the response over this? Normally I should have got a response which is somewhere over here, but what happens is I do not get any response over here. When I have a sufficiently large value, all of a sudden response comes up, that means I have a finite pressure oscillation to start an instability, and these are known as nonlinear instabilities. Therefore, we can characterize the instabilities further into, let us now put the whole thing together, combustion instability as happening from bulk mode oscillation. We have covered enough, we have done about it. We say it could be in the wave mode, it could again happen that it could be in the linear mode, wherein I am talking of small threshold values of pressure which excite it, non-linear, wherein a definite value of delta P prime is required to start an oscillation. Why is that delta P required? Because some losses have to be overcome, it becomes non-linear, but then I cannot use all these things together to get a feel for the problem. Therefore, but now the question comes, how do I, if I have understood the problem, all what we require as engineers is the rocket chamber must not go through a process of oscillation, it must not build up oscillation. How do I do it? One of the things is, maybe if I have a chamber, I add energy to the chamber, and what did we tell ourselves? Rocket chambers have huge energy. If I can reduce the amount of energy, like into the propellant I add some water such that I decrease the rate of energy which I put in into the oscillation, then it is grow. Therefore, I can say I can prevent an oscillation by reducing the energy rate of release. That means 1, reduce the energy release rate. From propellant. This is one. What is it you are doing? You are essentially having some gain in the energy, the oscillation is gaining some energy from the propellant. Therefore, what is it we do is you reduce the gain. Let us take a simple example. I switch on a TV, I want to increase the volume, I increase the gain, I hear something loudly, I reduce the gain such that my input energy itself is reduced. Second is, I sort of detune my chamber. What do you mean by detuning the chamber? After all, combustion is occurring, we said combustion happens maybe at a response frequency of so much, and now when my frequency of combustion and my frequency of chamber are same, I get oscillations. Therefore, just the same way wherein I tune to different frequencies for different signals, I maybe, if my chamber is like this and it is in the axial direction, maybe I make this chamber a little shorter such that now I increase the frequency of my chamber, keeping the combustion frequency same. Therefore, I detune my chamber with respect to combustion, and that is one way of avoiding instability. Therefore, the basic process of avoiding combustion instability are either you reduce the gain coming from the propellant, or I make the frequency of the chamber different from this. How do I make the, see, it is very difficult to reduce the length or change the diameter. What is it we do is we put something like what I show here. Either you change the dimensions of the chamber, maybe I change the configuration of the chamber such that I distribute the combustion in a different way away from the antinode into the node. I put something like a baffle, that means in the chamber I put some protrusions here which are like a baffle, and when something is rotating in the tangential direction, it breaks it up, it increases the frequency of the standing wave in the tangential and radial directions, and therefore I sort of detune my chamber. I can also have something like, I put something like a Helmholtz resonator, I put some other resonator here, and such that I change the frequency of this, maybe I put a different frequency here, I get a net frequency which is different, or I put something like a tube or a opening over here, I put an opening over here such that I increase the effective length and change my frequency. These are known as quarter wave tubes. Or one of the things which the Russians seem to follow is something which is of interest to us, and that is what I show in the figure here. If I have a chamber like this, I have a nozzle which is like this. If I can make the convergent much longer, that means I get the rate of density variations are quite smaller, because now my density variation for the same throat size, let's replot it. Initially this was my throat here, this is the area of my throat, I have a divergent. Now instead of this I delay it over here, I get something like this, and now I have my divergent here. That means my rate of density variations is much lower. I can allow some of the acoustic energy to radiate out, it is not getting into the stationary wave pattern and stationary standing wave pattern, and therefore my chances are there. That means I say I allow the nozzle to radiate out the wave. Well, these are some correction strategies. You know, this figure shows a opening here, that means I slightly change the tangential mode, because the dimensions being inside here I put a slot, the dimension increases, and this has been effective in reducing the combustion instability of one of the Viking engines or a 60-ton liquid propellant rocket. Let's go further now. We said there are different types of instabilities, and let's now talk in terms of the third type of instability, in which we said instead of the wave mode or the bulk mode of instability, combustion instability could also be caused by processes. What are the processes we are talking of? You know, let's consider fluid, let's consider hydrazine or MMH to be injected as a fuel, N2O4 to be injected as a oxidizer. You have variations in mixture ratio in the different parts. You remember we did the stream tube model analysis, and in some places I could have very good stoichiometric mixture ratio, in some places I could have something like a very lean mixture ratio, and therefore I could have variations of mixture ratio variations. In the region stoichiometry, the fuel burns readily, it creates wave motion, and this wave motion could lead to combustion instability, and very often the stoichiometric composition when heated is so powerful or creates explosions which creates wave motion, and this is known as popping. You hear popping type of sound, well, it couples with the chamber acoustics, and therefore you have popping instability, which is essentially due to mixture ratio variations. You also would remember that we talked in terms of solid propellant rockets. I told you it is all segmented rockets, segments are joined together, and whenever segments are joined together you have some inhibitors which are joining together. As the propellant burns, these segments get exposed, you have eddies which are being formed. If the frequency of these eddies coincide with the natural frequencies, well, I could have oscillations. This also we talked of. That means I have the second process which is segmented joints in solid propellant rockets. I could also think of something else. Let us think in terms of a new process, and this new process is, whenever I talk in terms of liquid propellant rockets, we have a large tank over here, large propellant tank, maybe liquid oxidizer, maybe liquid fuel, another tank with a common bulkhead here. Let us say this is liquid fuel, this is liquid oxidizer, this is supplying through pumps over here to my liquid engine, that is the thrust chamber over here. Now let us say under certain conditions, when the thrust is generated, I have the head of the propellant over here, and now I have, these are all columns, tank which is here. The tank can vibrate in the normal direction like this, it can oscillate up and down, the structure of this tank could vibrate something like this, and when it vibrates, the head of the fuel which is available at the pump inlet increases. Rather, let us say, let me draw a schematic diagram. I have a tank, the tank supplies fuel and oxidizer to my pump. From the outlet of the pump it gets into my thrust chamber which is the combustion chamber, and this is what produces my thrust force. Now because of the structural oscillations of the tank, maybe my inlet head to the pump changes, that means I get a modulation in the head over here. At the outlet, pump pressure increases, the modulation increases. When the modulation increases, I am supplying propellants at a modulated rate into the thrust chamber, and therefore my force changes. What happens to the force? Force further changes or gets in phase with the structural changes, and therefore I get a feedback because of this force into my tank. It increases the structural oscillations, and therefore my rocket now will go, it finds that some pressure is there, all of a sudden thrust increases, it jumps up like this and again comes back, again goes up, it goes something like in spurts. Instead of the rocket going normally like this, in a mission what happens is, under certain conditions it goes like this, goes like this, goes like this, like hopping. And a name of hopping is what we know as Pogo. I will show this in a slide. Let us go back and see this. Doesn't okay, see this is a large tankage is what is shown here. This is the pump, this is the nozzle, and let's see this is a buoy. This is a buoy on a stick. The stick has a spring over here, he puts on a pedal over here, there is a spring over here, this is he sits like this, and this is where I show this. This is the place where you keep your foot, this is where you keep your hand, and here you have a spring mechanism between this and this. Supposing I want to hop, he puts his hand here, he puts it together and is able to hop. This is known as a pogo stick. What is it we are telling? Well, I have a contraption like this, I have a handle, I hold on to the handle, put my foot over here, I have a series of springs over here, and this is what is connected to my bottom over here, and therefore supposing I want to go like a kangaroo, I go from here to here, I can hop like this, and in fact in many countries you have pogo stick races which are held every year, and therefore my rocket, instead of going up smoothly, goes in hops like this, and therefore this type of oscillation due to this process is known as pogo oscillations. And how do I have to control it? I must reduce the coupling between my pump and the thrust chamber. Therefore, maybe if I can put over here wherein I get these oscillations, I put some gas into the liquid. That means I put some small vapor bubbles into the liquid. Vapor bubbles can absorb lot of energy, and therefore I will not get these oscillations, and therefore I have something like a Pogo corrector, which I put over here and it corrects my oscillation. This is there in many missions, in all rockets or all launch vehicles we have Pogo correctors. And similarly, one of the points which some of you made was, how about sloshing? I have a liquid in a tank. See, the rocket is going up. See, it does not happen when you ground fire a rocket. This is a propellant tank. From the propellant tank I take the propellants, give it into the chamber. Now if the rocket is going up, I just get a straight axial load, but the rocket also turns and all that. That means I could get side loads, not only from the rocket, maybe from the wind bias, maybe I get the side loads. And then when I get the side loads, my surface of the liquid, instead of being plane, becomes it becomes a wave motion. And this wave motion, when it is traveling up and down, includes, again provides side loads to my rocket. And therefore what is it we do? We start getting side loads because the propellant sloshes, that is the free surface of the propellant changes, and therefore it becomes necessary for me to put some material, something like baffles over here, which will, because of the viscous dissipation, will not allow this to happen, and therefore I put baffles in my propellant tank to avoid sloshing. Sloshing is not a form of instability, but it is again with a mission, and the reason is the free surface area changes. You would not like these free surface changes, and therefore you put baffles to avoid sloshing. Therefore let us take a look at this baffles what are put for sloshing, and then we will conclude it. Yes, this is where it is. You put some baffles over here, and so that the liquid does not slosh, that is movement of liquid having free surface in a container, when it goes from side to side gives you a sloshing load, and baffles are used to prevent sloshing. Well, we will conclude whatever we have to say by saying, well, a liquid propellant rocket or a solid propellant rocket is susceptible to instability, and this instability could be defined in terms of bulk mode oscillations, or in terms of wave mode oscillations, or in terms of different processes. We did not get into details of solid propellant, wherein you could have oxidizers burning up giving you a particular frequency of depletion, but these are all details, and what we have covered is the basics of combustion instability. Therefore to summarize, in today's class we started with wave modes, we looked at the standing wave modes, we found out under what conditions a wave amplification can take place, and then we said, well, combustion energy is getting liberated and therefore instability can form. We also talked briefly about the process induced combustion instabilities. I think we stop with combustion instability here. In the next class we will start with maybe electrical propulsion, right. Thank you then.